Let us continue our discussions on the discrete Fourier transform. We saw that given x of n for n equal to 0, 1 up to n minus 1, the DFT is defined like this. And we saw that you need to consider only k for the indices 0 to n minus 1 because x of k plus cap n is the same as x of k. So, this is the DFT definition. Now, this can be written in compact matrix vector notation. So, let us define the column vector x, little x, which will be shown as boldface in typed or in printed work. So, in handwritten work we use an underscore here. We denote this as x0, x1 up to x n minus 1, and this is a column vector, and we are using the notation x suffix k. So, x suffix k really stands for x of k. So, to use this notation is more convenient in this context. Now, let us express this in matrix vector notation. Similarly, boldface cap x is denoted as x0, x1 up to xn minus 1 transpose, and once again x of k is denoted as x suffix k. Remember, for the kth bin index, the DFT is given by this, and this can be thought of as in an inner product of two vectors. One of the vectors is x as given here, and the other vector is e to the minus j 2 pi k n by n, and you can vary this over n little n going from 0 to cap n minus 1. You will generate a vector that is cap n long, and this definition of x of k can be thought of as an inner product of two vectors, and this is an inner product of two vectors for a particular value of k, little k, and therefore you can write all such inner products letting little k go from 0 to n minus 1. So, hence we have x of 0, x of 1, x of 2 up to x n minus 1. So, these are the DFT coefficients. For each value of k, you have an inner product. One of the vectors is fixed, and that is little x, and that is given by x0, x1, x2 up to x cap n minus 1. So, this is what is called as your data vector. The other vector is generated by e to the minus j 2 pi k little n by cap n, and then for each inner product you are going to vary little n. For a given k you are going to vary little n as given in this summation. To capture that, you can write this as e to the minus j 2 pi k n little n by cap n. So, along this dimension you are going to very little n. You are going to fix k and then you are going to vary little n from 0 to n minus 1, you will generate an n dimensional vector, and that when it is taken into an inner product with this vector, you will generate cap x suffix little k. But what you need to do is you need to do this for all values of k, and hence you can think of each row as being a function of little k, and hence in this dimension k varies. So, the DFT equation can be represented compactly in matrix vector notation. So, this can be written as cap x, and this is of dimension n cross 1. This matrix is called the W matrix, and this has dimension cap n by cap n, and this is your data vector, which is again a column vector, and this is cap n by 1. And this is also called as the DFT matrix, and the notation cap W is used because you can denote e to the minus j 2 pi n as W. This is the notation that is used in this context, and e to the minus j 2 pi by cap n is called as W, and hence these elements are nothing but powers of little w, because if you let e to the minus j 2 pi by cap n as little w, this is nothing but w power k n. So, this implies e to the minus j 2 pi by cap n times k n is really w power k n. Sometimes the DFT matrix is also denoted by w suffix cap n to make explicit its size. If the size is understood from the context, you can omit the subscript cap n. If you want to make the size explicit, you make the suffix explicit and show that it is of size cap n by cap n. So, this is a very compact notation, and one inference that can be made from this is that, remember, this is an n by n matrix and all the columns, right, are independent. They are independent because we have already seen that e to the j omega 1 n and e to the j omega 2 n are independent whenever omega 1 is not equal to omega 2, right. So, from that it follows that the columns of W are independent, and this is an n by n matrix with n independent columns, and if you recall from your linear algebra course, this has rank n, which means this is non-singular and hence invertible. So, W is called as the DFT matrix and has rank n, and therefore invertible. So, now we have the case that cap x equal to cap w times little x. So, this immediately implies little x is pre-multiply both sides by w inverse. So, this becomes w inverse times cap x, and you can show that w inverse is this. So, that is also an n by n matrix. It is e to the plus j 2 pi k n by cap n, and in this dimension k varies, and in this dimension n varies. So, you can think of little x, which is nothing but x0, x1 up to x cap n minus 1. So, this is nothing but w inverse, which is what you have seen just now. So, this is the W inverse matrix, and this multiplies the transform coefficients and you recover the data vector. So, you can go from data vector to the endpoint transform vector. From the endpoint transform vector, you can go back to the endpoint data vector via the DFT matrix. And you can easily verify that the inverse transform that was kind of given to you without any explanation, that really follows from the fact that the DFT matrix W has this inverse, and hence if you have 1 over n x of k e to the j 2 pi k little n by cap n, this is the definition of the inverse Fourier transform. All we are trying to do now is verify that this is indeed true, and this is almost trivially shown. So, this is 1 over n k going from 0 to cap n minus 1. Remember, we have to bring in little x into the equation because we are trying to show that this indeed gives you the original sequence that you started off with, and therefore, you can replace cap x of k by its definition, and hence this is L going from 0 to n minus 1 x of L e to the minus j 2 pi k L by cap n, and you want to use the dummy index L here because n is already part of this. You do not want to repeat that variable here because it will cause confusion, you will not get the right answer. This after all is a dummy index, that is why I am using L, and now I have e to the j 2 pi k n by cap n. Now, you can interchange these two summations without any worries because these are finite summations, and hence you go from L equal to 0 to n minus 1 x of L, and now look at this. So, this is nothing but 1 over n k going from 0 to cap n minus 1 e to the j 2 pi by cap n times k times n minus L. all I have done is I have collected all the remaining 2 exponential terms, and this is what this is. When L equals n, what will be this summation? Yeah, remember you also have to have this 1 over n factor. So, this will be 1. When L is not equals n, it will be 0. Therefore, the only term that will survive will be x of n, alright. So, this indeed shows that you get back x of n starting from this. So, the inversion formula is indeed correct. Now, there is another viewpoint of the DFT. We can think of the DFT as being samples of the DTFT. When we started off with the DFT definition, we just gave it as here is the formula, take it, right, no explanation was given, but now whatever we have seen so far has shown that this is consistent, that if you start off with this as the definition of the DFT, then you get this as the inverse and they are consistent. The only thing was, even though you do not make any assumption about the data outside 0 to cap n minus 1, moment you put the data into the DFT framework, you are guaranteed that x of n will be periodic with period cap n, which is also consistent with the fact that DFT is nothing but the DTFS written slightly differently, and the DTFT rather the DTFS assumption is the signal sequence is periodic. So, everything is consistent. Now, we can think of the DFT as the samples of the DTFT. For this, we make the assumption that the data are 0 outside 0 to n minus 1. So, here we assume that x of n equals 0 outside 0 to n minus 1, and now we will show that the periodicity of x of n will make sense as we go through this development. So, x of e to the j omega by definition is n going from minus infinity to plus infinity, x of n e to the minus j omega n, and this is where we are going to make use of the assumption that the data are 0 outside 0 to n minus 1. So, now the summation collapses to 0 to n minus 1 because x of n is 0 outside this interval. So, you have x of n e to the minus j omega n, and we know the interpretation of the DTFT. You can think of the DTFT as evaluating the Z transform around the unit circle. So, we get a continuum of values from 0 to 2 pi. Now, what we are going to do is we are going to take the DTFT, which is x of z evaluated along a continuum, namely 0 to 2 pi for as far as omega is concerned. Now, we are going to sample this. We are not going to evaluate the DTFT continuously, but we are going to evaluate this only at n points that are uniformly spaced, and hence we take x of e to the j omega and then evaluate it at omega equal to omega k, where omega k is 2 pi k by n, all right. This makes sense because the interval is 2 pi, you have taken n uniform points. So, the spacing between points is 2 pi by cap n and you are evaluating it at k uniformly spaced points, and hence you can call these samples as x of k. So, this is nothing but x of e to the j omega k. So, this is nothing but n going from 0 to cap n minus 1 x of n e to the minus j omega k. Omega k is 2 pi little k by cap n times n, and hence one interpretation of the DFT is taking the DTFT and evaluating it at a set of n uniformly spaced points in the interval 0 to 2 pi. All right. Now, if you sample in one domain, you periodically repeat in the other domain, all right. So, when we sampled in the time domain where the spacing was cap t apart, in the other domain the repetition was 2 pi by cap t, where cap t was the spacing. Now, the spacing is 2 pi by cap n, and hence in the other domain it has to repeat by 2 pi by the period, and hence you see that the repetition in the other domain happens with a periodicity of cap n, which is what we should expect, because just because you view the DFT as being samples of the DTFT, you cannot get rid of the periodicity. Therefore, even though we started off by saying x of n is 0 outside 0 to n minus 1, which is what we needed to restrict the summation in this range, moment you start sampling, immediately it introduces periodicity in the other domain, and that periodicity is exactly cap n. So, everything is consistent, right. So, this implies x of n equals x of n plus cap n. Again, the ideas that we learned from sampling in the time domain are applicable here. There you needed the signal to be band limited, so that when you sample the repetitions did not overlap if you did not want to cause aliasing. So, now here you are sampling in the frequency domain, therefore, in the other domain which is time, the signal has to be time limited. So, everything is consistent. So, the signal is time limited, you sample, periodic repetitions occur with periodicity cap n, and there is no aliasing. Yeah, question. Okay, actually I was going to come to exactly that question here. So, you raised it at the right time. When you sample at twice the set of points, you are sampling at a finer spacing. If you sample at a finer spacing, remember in the time domain, if you oversamples, the repetitions will occur later, and hence if you sample at say twice the number of points, here also the repetition will occur later, the periodicity will exactly be the number of points at which you sample. So, now suppose we sample at L points, which is greater than n, then the spacing is what? The spacing is 2 pi by cap L, and hence in the time domain the repetition will be 2 pi by L, which is L, and hence you are now left with the situation where x of n plus cap L equals x of n. Okay. And hence if you have, say, this as a sequence as an example, and if this is 0 to n minus 1, all right, or rather let me draw a different sequence so that you see the difference. Suppose I have this as my sequence. If I sample it at exactly n points, then what I will do is I will repeat this, and I will repeat this like this, and similarly I will cause repetition on this side because I am going to repeat periodically on both sides. So this is what my repetition will look. Now coming to the situation that you raised, now you are going to sample it at a larger number of points, and hence, so this is my original sequence. I am now sampling it at cap L, which is larger than n. So my repetition will occur with a periodicity of period cap L. Therefore, what happens at 0 happened at n in the previous case, whereas what is going to happen now is it is going to happen at index L. Therefore, the repetition will be like this. Which means from n to L minus 1 you will have zeros, right? All right. Yes. When you say time period, can you? No, remember we are sampling in the frequency domain, correct? In the frequency domain your interval is always 0 to 2 pi. So within 0 to 2 pi, what is your sampling period? You need 2 pi by cap n at a minimum, right? Because the signal is one way of seeing this is signal is time limited from 0 to n minus 1. If you sample it at n points, the repetitions will occur with a periodicity of cap n, which means the repeating periods won't overlap with each other, correct? That is the minimum. So which again correlates with the fact that you need time limited signal for you to sample in the frequency domain so that the repetitions do not overlap, provided you sample adequately. Now what you are going to do is you are taking the same 0 to 2 pi interval and sampling it at cap L number of points. So the spacing is now 2 pi by cap L, which is finer than 2 pi by cap n, and hence in the time domain the repetition will occur with a periodicity of cap L. So which is what is being shown here, right? So this repetition occurs later, consistent with the fact that you are now sampling it at cap L, right? So the sampling happens in the frequency domain. Does that answer the question? The other way of looking at this is we have already seen what a finer sampling does. The same thing can be obtained by starting off from the time domain. That is, suppose you have x of n which has DTFT x of e to the j omega, and x of n is defined for n equal to 0, 1 up to n minus 1, and it is 0 outside this interval. For this sequence you have this x of e to the j omega, alright, and hence x of e to the j omega is n going from 0 to n minus 1 x of n e to the minus j omega n. Now suppose I form y of n which is same as x of n for 0 up to n minus 1, and then I add zeros for n equal to n up to cap L minus 1. So this can be thought of taking a given sequence and zero padding it. Now what about y of e to the j omega? So this is n going from 0 to L minus 1. I now have y of n e to the minus j omega n, and this is easily seen to be n going from 0 to n minus 1. Not only that, within this interval y of n equals x of n. So this is times e to the minus j omega n, and this immediately tells you that y of e to the j omega and x of e to the j omega are identical. Now let us look at the corresponding DFT coefficients. X of k is n going from 0 to n minus 1 x of n e to the minus j 2 pi k n by cap n, and k itself goes from 0, 1 up to n minus 1. So the situation here is we have an n point sequence x of n, and we have computed its n point transform. So far so good. Now let us look at y of k. Y of k is an L point sequence, right. So this is n going from 0 to L minus 1, and this is y of k e to the minus j 2 pi k n, and this is cap L. And if you have an n point sequence, you get an n point transform. If you have an L point sequence, you will get an L point transform. So you will have L DFT coefficients. Therefore k itself has to go from 0, 1 up to L minus 1. So this is nothing but n going from 0 to n minus 1, and y of k is the same as, rather this should be y of n. So this is x of n e to the minus j 2 pi k n. This remains exactly the same. And therefore this is 0, 1 up to L minus 1. So this is exactly the same idea, but looking at it from the other point of view, that is we are starting from the time domain. So earlier what we did was we said let us take the DFT rather the DTFT and sample it at L points where L is greater than N, and then we saw that the repetitions occur later and between the repetitions zeros get added. The other way of looking at exactly the same concept is take the given sequence, N point sequence, zero pad it and compute the L point DFT. Again what this gives you is you get the samples of the DTFT. Remember, the DTFT is unchanged because the DTFT of both the original sequence and the zero padded sequence are the same as it should be. But what you have done now is by zero padding you have evaluated the underlying DTFT at a finer set of points. So, the DTFT remains unchanged, but when you zero pad you sample the DTFT at a larger set of points, that is the only thing that happens. So, either you can take this viewpoint by starting off with a given sequence and zero padding and then realizing that you have sampled the DTFT at a finer set of points, that is one way of looking at it. The other way of looking at it is what we saw earlier, you take the DTFT, sample it and then realize sampling it at a finer set of point means the repetitions occur later in the time domain, which is equivalent to zero padding. So, these are two sides of the same coin. And one thing to note in this context is, let us look at the case of the number of samples being odd or even, and if you take n equals 3, then you sample the DTFT at a uniformly spaced points. Here the spacing is 2 pi by 3. So, this is 0, this is 1 and this is 2. So, this is k equal to 0, 1 and 2, and in general this point will correspond to n minus 1 by 2 and this point will correspond to n plus 1 by 2. If you had even set of points, this is how the samples will be distributed. So, this is again k equal to 0, 1, 2 and 3, and this point will be corresponding to n by 2. So, when you sample the DTFT at an even set of points, you will have a sample at omega equal to pi. Whether n is odd or even, at omega equal to 0 you will always have a sample point. Whether you get a sample point at pi or not depends on whether the number of points is even or odd. If it is even, you will hit the omega equal to pi point, otherwise you will not hit that point. And in this context, it is very important to realize that x of n equals x of n plus cap n, and it is also the case that x of k, which is the DFT coefficient, that also is periodic with period cap n. So, one immediate consequence of this, we have already seen this before when we are looking at discrete time periodic complex exponentials. Here, because of the periodicity, the index n is really index little n mod cap n. Because no matter what the index is, you can always map it to the interval 0 to n minus 1. Similarly, here the index is really index mod cap n, because both of them are periodic with period cap n. Therefore, both the sequence index and the transform index are index mod cap n, and hence this index is also the same as -1, right. Similarly, this index also is the same as -1. And moment you understand what is happening here, if you want to convert the DFT frequency to true frequency, first of all, to do that you need the sampling frequency information, and when you sample in the time domain, you periodically repeat in the frequency domain. Therefore, we saw that as far as the spectrum goes, the spectrum is periodically repeating, and hence if you think of this in terms of hertz, this will repeat periodically with a period of Fs, right. That is, I am talking about x s of cap f. I am showing now this in cap f. Earlier we had seen this as x s of cap omega, and we denoted, instead of Fs we denoted this point as omega s. All I have done now is I have scaled it by 2 pi so that the repetition is Fs rather than omega s. We also know that when this is mapped to the DTFT, this Fs will get mapped to 2 pi. Now our goal is to convert the DTFT to back to true hertz, but in practice we will only be dealing with the DFT because that is the only thing that is machine implementable. Therefore, we cannot compute the DTFT on a machine, we have to compute the DFT. But what are we doing as far as the DFT goes? We are taking the interval 0 to 2 pi and dividing it into n points. Therefore, we are dividing this into n points. The penultimate, the last point is really n minus 1, and if you let k to be n, that is the same as k being 0. Therefore, k being n will correspond to the point 2 pi. Therefore, the general point on the DFT bin index is k. Now, given the kth bin index, suppose you want this to correspond to true frequency, right, you need to divide by n, and then what else do you need to do to get the true frequency in hertz? You need to multiply by Fs, and hence if you take the kth DFT bin index, if you want to know what frequency it corresponds to, divide by cap n and multiply by Fs, this will give you that bin index's true frequency location. So, this is how you convert bin index to true frequency, right. So, everything is consistent with what we have seen so far. Let me see if I can quickly show this in MATLAB. Suppose I have n going from 0 to 15, I have 16 points, and then I am evaluating, rather forming a sinusoid with frequency of 1 kilohertz, and then sampling frequency is 8 kilohertz. So, I have x of t, which is sine 2 pi f naught t, and I want to form x of n, which is sine 2 pi f naught. I am going to take it as 1000 hertz, and I am going to sample it at 8 kilohertz. So, I am going to replace little t by n cap t. N cap t is 1 over Fs, and this is what I have. So, this is the sequence I want to generate. So, I have sine 2 times pi times n times, now I have the normalized frequency which is 1 over 8, 1000 hertz by 8000 hertz. So, this is my sequence, alright. Now, I want to compute the DFT, and the corresponding command in MATLAB is FFT. So, I have FFT of x. So, if you do not give any argument, it will compute the endpoint DFT which is 16 points here, right. Now, remember this is a real valued sequence, therefore, 0 to n by 2 is all that I need, because from n by 2 plus 1 to n minus 1, because of symmetry, it will be the complex conjugate version of the first upper half of this, and hence I need to restrict x only from 0 to 8. MATLAB is 1 based index, therefore, I restricting it to 1 to 9, and now I need to plot this, alright. So, I will use the stem command, right. Now, I am going from 0 to n by 2, right, alright. So, I need to divide this, remember I need to do k by n. So, this is 16 times Fs, Fs is this, okay, and then ABS x. Okay, so this should actually so the x axis is frequency. So, this goes from 0 to Fs by 2, because from Fs by 2 to Fs is just the magnitude plot will be the same, and now the sequence frequency was 1 kilohertz, and you see at this point a value of 1, at every other bin index the value is 0. So, we will continue this example in the next class, we will see why the other values are 0 here, and then what we will also do is we will sample the DFT. Right now we have sampled it only at 16 points. We had a 16 point sequence, we had a 16 point transform. Now, we will 0 pad and then get the DFT by 0 padding, and then overlay those plots on this and see the connection, and then we will compare this with the DTFT, and then we will convince ourselves that the DFT is indeed the samples of the DTFT.